In this video, we're introducing uniform circular motion as the beginning of our circular motion discussion. We're going to start, as we did with all of physics this year, at talking about kinematics, right? The what is moving, how is it moving, and we'll get to the why next. So when we talk about uniform circular motion, there are a couple of things we mean. We really need to focus on uniform, because I think we all know what circular is and we know what motion is. But what's uniform about it? It turns out the speed is what is uniform. As you spin something over your head, like this picture, the speed of the object stays the same, right? And how do we measure the speed? Well, distance over time, of course. But when it comes to a circle, the distance is completely dependent on the radius of that circle, and capital T, not lowercase t for time, but capital T, which is what we call the period or number of seconds it takes to go around a full cycle, is what we need. So how does that look? Well, the speed then is 2 pi r over the period. Remember, this is for uniform circular motion only, or it is the average speed for any circle. But for uniform circular motion, that's the constant speed. So if you think about holding a yo-yo and then swing it over your head, as we did in that previous picture. If you imagine a yo-yo that, say, has a string 1 meter long and it takes 2 seconds to make a full cycle, it's kind of slow, then the speed would be 3.1 meters per second. Now, a lot of circular motion is actually not uniform, and we can still use what we learned from uniform circular motion to help us with it. But if you were spinning a yo-yo in a vertical circle, it would slow down as it goes to the top and speed up as it goes to the bottom. More on that later. That's usually more easily talked about with energy conservation. But speed is not constant, so we can't use this relationship. We will, however, talk about it in terms of forces in a little bit. So another question then comes, well, we talked about the speed, but what about the velocity of this object? Well, velocity has direction, and as it turns out, velocity is always tangent to the circle. So the direction of velocity is not always the same, but the speed or the magnitude of it is. And this is what that means for a circle is that it's perpendicular to the position vector, which is the r vector pointing to where the object is in the circle. And we can think a little bit about this if you imagine standing on the Earth, right? If you were standing at, say, the North Pole, up in the Northern Hemisphere, right at the equator, we could do the opposite in the South Pole and the Southern Hemisphere spot. But who goes fastest on the Earth? Well, the Earth is all spinning together. So what matters is the radius, because the period for everyone on Earth is 1 day. Right? So the person on the equator with the biggest R goes the fastest. What about on a merry-go-round? Which horse will be actually traveling the fastest, the inner horse or the outer horse? Well, for the same reason, since the period is the same, the whole thing goes around once in a certain amount of time, the outer horse with the bigger radius or distance from the center will be going fastest. But what about the planets? Which planets move faster? If you know anything about the solar system, you know that it's actually the inner planets that travel around the sun fastest, not just in the shortest amount of time, but also with the highest velocity. But this is different than what we just said. And the reason for that is the planets are not all moving together. They do not have the same period. They are independent objects. We'll talk a lot more about planetary motion when we get to gravitation, which we will talk about in a little bit. But because they have different periods, that's why. So is this yo-yo accelerating? Well, it's in uniform circular motion with a constant speed, but of course, constant speed with a changing direction is still an acceleration. Velocity is a vector. It's always changing its direction, so that has to be acceleration. Uniform circular motion is a special case of acceleration at constant speed. There are some other things we could talk about, but this is the one that we're looking at right now. How else could we talk about this object accelerating? We don't just have to use kinematics relationships. We have another argument for that, and that is a forces argument. If you think about Newton's laws, you know that if something is changing direction, something must be pulling it, because if there's no net force, things would travel in a straight line. So the tension, the string pulling on the yo-yo or the object, is that force of tension is the net force. And so we talk in this term, there's this word we want to introduce called centripetal. Centripetal means center seeking or toward the center of a circle, and it has a type of acceleration we call centripetal acceleration. And of course, like any, quantity in kinematics, we want to know the magnitude of it, and we want to know the direction since acceleration is a vector. If we were to try to do it this way, we'd be in trouble, right? Because the velocities there, this is assuming that the velocity's magnitude is changing and that it's staying in the same direction. But that's not what's happening here. And v final and v initial, just the magnitudes of the velocity, the speed, is the same all the time. So we would have no acceleration. But that doesn't fit with our definition of acceleration. So we need to find delta v in a different way. We have to actually draw it out as a vector diagram because it is indeed a vector. And so if we watch an object going around, we've got v1 and v2 here, and the delta v would be v2 plus negative v1, which would give us a delta v. And you notice that delta v is pointing toward the center of the circle. This delta v then, the change in velocity over time being the acceleration, is in the direction of the center of the circle. You can use some similar triangles and make some arguments here to point out that delta v over delta r is the same ratio as v over r as time gets very, very small. Delta r is basically the arc length delta s, as that's going on. And so we find that we can keep working through this, and the centripetal acceleration, by definition, is delta v or delta t, which ends up being v squared over r. Now, I'll say, you don't really need to follow that derivation too closely. You can go back and look at it. Your textbook has a version of this as well. But the big idea here is that the centripetal acceleration can be given as v squared over r. The units come out as acceleration. And we can start thinking about maybe that yo-yo problem again. Right? If I have my 1 meter long yo-yo, 2-second period, a speed of 3.1 meters per second, I can find the acceleration, v squared over r, which ends up being 9.6 meters per second squared. We can do a lot more of these as another yo-yo. Now we have a 1 meter long yo-yo, makes 2 cycles in 1 second. What is v in a centripetal? Well, v is 2 pi r over the period, and the period is half a second, because 2 cycles in a second, so half a second per cycle. And then v squared over r gives us 160 meters per second squared, or about 16 Gs. We have one other piece we need to talk about with centripetal acceleration, and that's its direction. We already talked about how the delta v part is pointing toward the center. And so if those two things are vectors, time is a scalar, then those two vectors must be pointing in the same direction. And we already said that delta v was in toward the center of the circle. Right, so delta v always points toward the center of the circle, and therefore a centripetal always does as well. Right? It's radially inward is usually the direction we talk about. So you can also think of this in terms of the net force causing this acceleration, and hopefully it makes sense that if the only force acting on this object, other than sort of gravity pulling it down, which we're going to ignore right now, is the tension force inward, well then of course the acceleration should be in the direction of the net force. So what are the vectors? Position points from the center of the circle out to the object. The velocity vector is tangent to the circle. The acceleration vector is radially inward, so opposite direction of the position vector. And the centripetal force, which we will talk about more next time, is also pointed toward the center.